Of course, that may kind of depend on you guys. Okay, so all we've discussed so far for you watching the video is concave up and concave down. Concave up is part of a smiley face. Concave down is part of a frowny face. Notice that these graphs are decreasing and these graphs are increasing. The little guy on the right is just another sort of graphical representation for you. Everybody on the left, what kind of concavity is that? Concave down, because it's part of a frowny face. And everybody on the right is concave up. And notice what it says in here. F double prime means what? Second derivative. Concavity comes from your second derivative. So the places on the graph where that second derivative is negative or less than 0, it's going to produce a concave down. Part of graph from the original graph actually will have a concave down sort of shape. There's an actual definition of concavity if you want to see it on page 190. You can read sort of the mathematical language for the test for concavity on page 191 if you want to. The steps for finding concavity, and I should have taken out that one, that's kind of a typo, but you always want to address first, and I forgot to put this in here, is you want to address the continuity of your function, or where it's maybe not differentiable or something. So you want to address that first, and then you got to go into everything else. So let's look at our steps and kind of read them through as we kind of work through the problem. The problem says to determine the open intervals where the graph is concave up and concave down. This is going to look a lot like finding increasing and decreasing, but we're using second derivative. So our first step is it continuous? Is it differentiable everywhere? Are we okay on this? Yeah, it's just, we know it's going to make a parabola, basically. It says to find the second derivative. So we can do that. First derivative is 2x minus 1. Second derivative is 2. Then it says to set it equal to 0. Is there a problem with this? This one is just constant. It's always 2. So when you go to do your number line, little test or whatever, your little number line, there is no critical number to put on here. Because no matter what you quote-unquote plug in, you're going to get a positive 2. So what does that tell you about the concavity for this entire graph? The whole thing is concave up. And no sharp corners, right, Brandon? So the whole thing is concave up from negative infinity to positive infinity. It's basically what that's telling us. Any questions? Concave up means that the entire graph is going to be part of sort of a large smiley face. Good question. All right, next example. Same kind of deal. We need to think about, though, where this thing might be not continuous. Do we have an issue with tangent? Doesn't tangent, the graph on its own, look like this? Yeah, we've got some asymptotes. Do you remember where those are? Pi over 2 and negative pi over 2. Which, notice those are our endpoints. So as far as our interval goes, we're okay. Just as long as you remember at pi over 2, there will be an issue there. So let's go ahead and take our first derivative. Derivative of 2x is 2. What's the derivative of tangent? Secant squared. So I have minus secant squared x. Second derivative. Derivative of 2 is 0. Now, for some of you, it's going to help you to think of this little guy right here. I don't know if you can see that. Can you see that up there? Sort of. As negative secant x, the quantity squared. Sometimes it's easier for kids to see what to do if they write it like that. It means the same thing. So you bring your 2 to the front so that I have a negative 2 times secant x. And rather than having the exponent squared, it's now to the first power. You have to finish the chain. Right. Now we do the derivative of secant, which is secant x tan x. Good. Does everybody see what happened? We perform the chain. This was the derivative of the outer function. This is the derivative of the inner function. So now we can sort of shove it together. so that we have -2 secant x or secant squared x, quantity squared, whatever, tangent x. According to our little steps up here, what do we do next?
0.
Set it equal to 0. Divide both sides by -2. Now this is a little bit sticky. Or is it? Isn't this a whole lot like if I had 0, this is just an example, of like x plus 3 times x minus 2? Isn't it just two things being multiplied together that are equaling 0? It's a product here. So can I just split them apart? Sure you can. This isn't even how I did it on the first video, but it doesn't matter. It's the same thing. Secant, of course, if you unsquare it, if you square root it, we're still looking for where secant is 0. Where is secant 0? Think about the graph of secant. What does it look like? Does it cross the x-axis?
No. Nowhere.
It doesn't. So I think we're a little bit at a dead end, aren't we? What about tangent? Isn't tangent sine over cosine? So if you can't remember where tangent is 0, can't you just figure out where sine is 0? Won't those be the same places?
0 and 360.
0 and how about pi?
Well, you're using x, so she assumed degrees.
Is pi in our interval? No, it's not, but that would be a place. So we don't really care so much about pi. We're just concerned about 0. Anything else? Okay. What about this cosine guy is on the bottom, which really that's cosine is on the bottom. Do we have an issue where maybe cosine shouldn't be 0 so much? Where is cosine 0? Pi over 2? Negative pi over 2? All the same places where secant would be undefined? Right? And it's not in the interval either, so I think we're probably okay. So 0 is kind of our little issue here. So now it says to do the number line little test. And here's what I'm going to strongly suggest. Hang on a second, Brandon. I'm going to label this f double prime of x, because pretty soon you're going to start to have a couple of number lines going at the same time, and you need to know which is which. Yes, sir?
Why does it matter if secant and cosine are not in both or only concerned about tangent?
Whenever you split these apart, well, if there was a place where secant equals 0, it would make the whole thing 0. Brandon.
I'm sorry, not secant. Sine.
Because you could leave it tangent, but if you did not remember where tangent was 0, you could make that sine over cosine. It's the same thing.
But like, why does it matter if
Isn't
sine
sine
is not on the interval?
Right. If sine is 0, the whole thing is 0.
And then cosine of 0 is sine of it.
Correct. Did we even answer your question, Brandon? Maybe I don't understand your question. What is your question?
Alright, like, if sine isn't on the interval, why does it matter? Because it's going
What do you
to
mean
divide
sine's not on the interval?
on the interval of negative 2 pi.
That doesn't make any
If
sense.
that's the required, it has to be within the
But I don't know what you mean that sine's not on the interval. That doesn't make any sense.
Okay, you know how you got pi and 0 equals x for sine?
Mhm.
Pi is not on the interval.
Right.
You crossed it out.
Right.
Why did it cross it out when, if you divided it by cosine, it could still be in the interval?
Because it's still no. X has to be in the interval.
Like,
It makes sense.
Not your total, not your y value, not once you plug pi in. But they want to know, they want x's that are on this interval. Those are x's.
Except for pi, now you split things, even if it's things sine, what you do for sine divided by
Yeah, it's not going to, this would produce a y value that may or may not be on the interval. They're not concerned with that. They want your x value to be in the interval. I don't know how to say that any different. Right, you wouldn't be able to use those endpoints. But secant and cosine are undefined in the same places. So the same answer over here for undefined for secant is going to be the same for cosine. Oh, wait. Where cosine is 0, yes, secant would also be, yeah, correct. Brandon, did that make any sense at all?
I'll just know not to.
Okay. For now, I think it'll click later. So if we take a -1 and I plug it in, where am I going to plug it into? Which one? Second derivative, because this is the number line for second derivative. And I think because we're doing trig functions, let's not do -1. Let's do like, I don't know, negative. Well, we need to stay in our, our interval, so let's do like -π/4 maybe. So we're plugging in second derivative. Now here's what's kind of nice about this. We're only concerned with the signs, not so much the numbers. So if I have all students take calculus, and I'm talking about -π/4, that's the fourth quadrant. Is secant positive or negative?
Negative.
And you're squaring it anyway, so it doesn't matter. No, it's going to be positive. So negative times a positive times, is tangent going to be positive or negative? Negative. So negative times negative is a positive. All right, let's look at the next little section over here. If I put in a positive π/4, isn't everybody positive? So I have a negative times a positive, and I get a negative. So now we can talk about the concavity of the graph. So it is concave up, or part of a smiley, from 0 to π/2, because that's where they told us to check it out, and concave down, and you can use words, I just use arrows because it's faster. From -π/2, I don't know if a professor would like that or not, though, so listen to your professors. To 0. Yes, I did just do it backwards, didn't I? Dang it, sorry. Plus sign is positive. I'm sorry, don't be mad. Thank you, good catch. Alrighty, next one. Flip the page over. So that was the concavity piece on its own. Now they're going to introduce one more thing to you. We've talked about this phrase before. Point of inflection, you know what that means. You can look at page 192 and you can see all the math words that sort of explain it. The translation is it's the point on a graph where the concavity changes. So in other words, if we've got a graph that's concave down and then it changes to concave up, that point right there would be a point of inflection. See how we have like part of a frown and then part of a smiley? So that's what's happening there. It does say that if this point is a point of inflection of the graph, then either the derivative equals 0 or the derivative doesn't exist at that place. It's either one or the other. So let's see here. We're going to find the points of inflection and discuss the concavity of the graph. So discussing the concavity, you can do that. We just did that. Points of inflection, that's a little different. So let's look and see. First of all, are we sort of continuous here? Is there anything x can't be? Do we have any issues? We're fine, right? So let's go ahead and find second derivative. Half of 4 is 2. We lower the exponent by 1. Plus 3 times 2 is 6. Lower the exponent by 1. Second derivative, we get 6x squared plus 6x. 12x, my bad. I just started looking at that going, I don't remember that. Thank you. 2 times 6 is 12. Now what do we do? Yep, set equals 0. Good. I'm going to go ahead and factor a 6x out of both of those. So I have x plus 2. So what would x have to be in order for that to be 0? -2 and 0, right? Number line? And I'm going to label this as my second derivative number line. And then we plug some stuff in. If I plug in a -3 into this right here, am I going to wind up with a positive or a negative?
Positive.
Is she right? Okay. If I put in a -1, am I going to have a positive or a negative? Negative. If I put in, say, like a 2, am I going to have a positive or a negative?
Positive.
And now you can see your points of inflection. Neither one of these were places that were undefined. So those are our points of inflection because we changed from concave up to concave down and concave down to concave up. So I'm going to abbreviate and put POI for points of inflection. One of them is at -2 comma something. The other one is at 0 comma something. How do you get the something? Into the original. Good, because we're talking about the original graph. They want to know where's the point of inflection on the original. That was the whole point of doing all that. So we take -2, we plug it into the beginning, work through the math, and you're going to get -8. Take 0, plug it in, you get 0. It also says to discuss the concavity. That basically just means list out where it's concave up and concave down. I'm not going to make you write full-out sentences. However, it'd probably be good for you. So we have concave up and concave down. Concave up. It's from -infinity to -2 and 0 to infinity, because that's where the plus signs are, right? Concave down is -2 to 0. How are we doing? Do we have questions? Are we okay?
So we don't have to say if it's like concave, increasing, or decreasing.
Nope, we're going to start putting all that together on Friday. So we're only concerned with concavity, not whether the graph is increasing or decreasing at this point. But I did just want you to see the pictures at the very beginning so you kind of see what they look like.
So every time that is more than 2 and like it changes positive, negative, positive, negative, positive, negative.
It's a point of inflection, unless the only time that's not true is if that point is a place where it's undefined.
Okay.
You know what I'm saying? And the reason, Marina, is because let's say x is not allowed to be 1. So at 1, there's some sort of asymptote. So that means that graph would have done, I don't know, I'm making this up, something like this. Which tells you that that would not be a point of inflection. It would just be in that. Yeah. All right, so let's do the next one. First of all, is there anywhere where we have an issue with sign? Or are we continuous? Are we differentiable? Are we okay? Yeah, sign's fine. So first derivative. I heard cosine, good. Cosine of x over 2, and that's it, right? No, thank you.
You got it.
Yay, derivative of the inside. So the outer function, we get cosine. What's the derivative of the inner function?
It'd be
Remember, x over 2 means a half times x. They're the same thing. So what's the derivative of the inside? A half. And I'm going to put it in the front because it just looks better up there. That's where it belongs. Second derivative would be 1/2, then what? Negative. So I'm going to put my negative in the front, and it's sine. Don't touch the inside yet. Then what? Finish the chain. So, okay, this first half came down. You can just bring that down. Because it's a constant. If you wanted to do product rule, you can, but it's going to become a 0 somewhere, and that other half goes away. So we just bring down our constant. Derivative of cosine is negative sine of the angle. Now we need to multiply the whole thing by derivative of x over 2, which we said was a half. So I rewrite it as -1/4 sine of x over 2. Now what? Equal to 0. Okay, where are my places where sine is 0? 0, pi, 2 pi, 3 pi, 4 pi, and I'm going to stop there because so far I'm within the interval, and I think we're going to be able to shave some off here in a second. That's what x over 2 is. How do I get rid of that divided by 2? Multiply, right? So we multiply everybody by 2. 0 times 2 is 0. Pi times 2 is 2 pi. 2 pi times 2 is 4 pi. And now I'm going to stop there because that's within our interval. The x values have to be within our interval. So I don't need to mess with 3 pi or 4 pi up here. They ended up not making x on the interval. All right, so we draw our number line. Yep, good question. So we've got our little number line, and I'm going to label it. It's a good habit to get into because things are about to get a little bit more crazy. Now we take values in between here and we plug them in and see what we get. Where do I plug them in? Second derivative, because it's a second derivative number line. So if I take, say, like a positive pi, and I shove it into the second derivative, it's really sine of pi over 2, which is sine of 90 degrees, which is 1, times negative a fourth is a negative. Isn't 3 pi the same thing as 1 pi? Yep, it's just a whole circle later, so that's also negative. Let's put in like a negative pi. That would be sine of negative 90 degrees, or sine of 270 degrees, which is negative 1. Negative 1 times negative a fourth is a positive. And would, I'm sorry, what? Everybody okay? Negative pi over 2. Don't forget you've got to do the divide by 2. But do you see how 0 and 4 pi have brackets? They're including 0 and 4 pi, so you're going to have to be able to tell if that's a point of inflection or not. How would plugging it in tell you? Right. Right, because there's brackets on those, they're including 0 and 4 pi in the interval. So it's possible that 0 is a point of inflection or 4 pi is a point of inflection, and the only way you'd know that is if you tested the opposite sides. Okay? So if we put in 5 pi, what happens with 5 pi? But we still have to test it because I need to know if 4 pi is a point of inflection. Does that make sense? Look at. Isn't 3 pi 270? 3 pi over 2? Oh, which would make that negative 1. Whoops, sorry, negative 1 times. You're right. Thank you. Good catch. So then 5 pi is going to be what? It is a negative. If you plug it in, you get a negative. Mm-hmm. I think what happened on the 3 pi is I did what Jacob did a second ago. I put the 3 pi in and I forgot we were doing divided by 2. So be careful. That's an easy mistake to make apparently since Jacob and I both just did it. Alrighty, so now we can kind of tell where we have points of inflection. Every one of these is a point of inflection. How come? Concavity changed. So points of inflection are going to be at 0 comma something, 2 pi comma something, and 4 pi comma something. How do you know what the something is? Into the original. I love that. So 0 into the original would be sine of 0, which is 0. Isn't 2 pi and 4 pi the same thing as 0? Yeah. In radians, in the same place on a circle. So aren't these all probably 0? Yeah. So there's our points of inflection.
How would you, when you're doing the little chart,
Uh-huh.
how is there a way where it would be the same size? How would that look like?
What it could be is like perhaps
Would it be like it goes
like
into a cave and then like takes a right?
it'd look like this, like if you had like a parabola or something, like this would be a critical point because it's a minimum, but this is concave up and this is still concave up.
Okay.
And it's not a point of inflection. So you'd have a positive for both of those in a row. Good question. So concave up, we've got, do I need to include the negative infinity to 0? No, they only asked us about this interval. So for concavity, concave up is going to be from 2 pi to 4 pi. And concave down is going to be from 0 to 2 pi. Why don't I have brackets on those?
Should we just put like CU and CD?
No, I think that's going to be too short. Don't do that. Good question, but me. The reason is because is that right at 4 pi is where it changes from concave up to concave down. So it's a point of inflection, which means it's neither up nor down. Does that make sense to everybody? So that's why there's no brackets, because it doesn't include 4 pi. So everything going right up to 4 pi as close as you can get without actually being 4 pi. Remember, are you okay?
Yeah.
You're just thinking on it. I get it.
So you never,
Process.
You never do brackets?
It depends. In this case, we wouldn't, because 4 pi is a point of inflection, and it's changing. So right at 4 pi, it's neither. So you can't count it as concave up.
Okay.
Does that make sense?
Yeah.
Okay. Good questions. All right, second derivative test. Now this is where, if you want to memorize the math words, go for it. I think it's confusing when you do that. You can kind of draw out the picture, and it sort of is going to make more sense. And you can see the actual definition on page 194. If you have the second derivative and it's greater than 0, in other words, it's concave up. Think about this. If I draw concave up, that point right there, have I found a relative max or min? I found a min. It's a minimum. So be careful, because that's going to be a plus sign. It's greater than 0. You're going to want to put max. Please don't. It means concave up, which means a minimum. So in other words, so let's flip it. If it's less than 0, it's a negative, meaning concave down. So that point would be considered a relative max. Does everybody see how that works? It'd be smart to draw that picture. Okay, so Sarah, if the second derivative is greater than 0, it's positive, like up here. We said concave up. So if it's concave up, it makes a smiley, which means at that point would have been a minimum. It's a low point. Okay, here's the other thing you have to know. If the second derivative at whatever point is 0, we don't know if it's a max or a min. We're not sure what's happening there, and the test fails. It's inconclusive. So you would have to go back and use the first derivative test, and sometimes that'll tell you something, and sometimes it won't. So, and also, I realize some of you guys are like, why would we use second derivative test for min and max when we could just do first derivative? Isn't that what we did the other day? Yes, it is, and sometimes you're not going to be able to do that. There are some questionable problems that are out there, and there's an AP test question running around out there where you don't have a choice. They force you to do the second derivative test and then go back and do the first. So just be prepared for that. They ask you for it, you have to do it, and in your book it's going to ask you to do second derivative test. So that's kind of where we are here. So you just have to follow directions. I wrote up some steps for doing your second derivative test. All of those steps are preceded by checking for continuity and differentiability. And this is where it's a little bit different, because we're not going to do that fancy little number line we've been doing. All right, let's go ahead and look at this. First derivative, set it equal to 0 and solve. We've been doing that. We can do that. Let's do it. First derivative, it's 6 minus 2x. Set it equal to 0 and solve. We can do that. And now we have a critical number, 3. Do not draw a number line. I know your pencil wants to. Please don't do that. It's hard for me to not do that. Like, I'm in the habit. Like, I have to go, oh, wait, it's different. So at 3, something happens. Third step, find your second derivative. Okay. Second derivative is going to be what, -2? find f double prime. Sorry, I left out a little double prime. I need to retype these for next year. F double prime. Find f double prime, second derivative, at the critical numbers. So we're actually plugging the critical number into the second derivative. If you get a positive,
There's nowhere.
wait, f or double prime? Hang on. Yes. If you get a positive, the critical number is at a relative min. If it's a negative, it's at a max. If you get 0, it's inconclusive. So the problem with this is we don't have a variable to plug it into. But this is our notes, so I'm going to go ahead and finish writing it out. If you take 3 and you plug it into the the second derivative, what do you get? -2. A negative, indicating concave down, which means at 3, what happens? It's a relative max. So you have a relative max at 3 comma something. Is it 3 -2? Nope. Where do I plug the 3 into? The original, because we're talking about the original. We plug in a 3 here, and I believe we get 9. And if you need to, draw yourself a little arrow so that you know what you plugged it into. Next one. Alex, sit up. Do we have any issues with differentiability, continuity? Are we okay? We're okay, so let's keep going. First derivative. What's the next step? Equal to 0. I've had lots of questions today about solving problems like this, like how to get x by itself. What do we do? Factor. Okay, I usually tell you guys, but I'm starting to think maybe I shouldn't tell you. I'm going to factor out 4x squared, and I get an x minus 3. So what is x?
3 and 0.
3 and 0.
I know how to do it now.
Good. I'm glad. I know you want to do a number line, but what are you supposed to do? Find the second derivative. They're forcing you to do the second derivative because it says so in the directions. Second derivative is going to be 12x squared minus 24x. Now what do we do? Good. Emily's got it. Take the critical numbers, plug them into the second derivative. So I need to find the second derivative at 3 and the second derivative at 0. If I plug in a 3, I get 36. If I plug in a 0, I get a 0. The 36 is a positive number. What does that tell me? It means it's concave up, which means that I just found a minimum. So the relative minimum at 3 comma something. How do I find the something? Plug it into the original. And whenever I do that, I get negative 25. What happens when I get a 0? Right, it's inconclusive. We don't know. So we go back and do the first derivative test now. Now for the first derivative, we already found our little critical numbers. Again, the directions said we had to use second derivative test. They're forcing you to do it. So we have 0 and 3. We're going to test all around it. If I put a -1 into, where do I put it? First derivative, because it's a first derivative number line. If I put a -1 in here, do I come out with a negative or a positive? Negative. What if I put a positive 1 in there? Still a negative. There you go. What if I put a 4 in there? Positive. So if this thing is decreasing and decreasing and then increasing, well, we already know that that's a relative min. It looks like it's 0. As far as we can tell, nothing really happened. So we're good. Here's our relative minimum, and you're done. Alrighty, next one. Is this the last one? Yay! Alrighty, first step, what do we do? First derivative. First of all, is there anywhere that we know of where this is discontinuous or there's a problem? I don't think so. I think we're probably okay. First derivative. Derivative of cosine is negative sine. And then derivative of negative x is negative 1. Now what? Equal to 0. Good. Add 1 to both sides. Divide both sides by a negative. We've got to think about what angles produce a negative 1 when we're talking about sine. Remember, it's cosine comma sine, so it's where the y value is negative 1. 3 pi over 2. Good. Now, are there more answers than that?
Yeah.
Yeah, because we're going all the way to 4 pi here. So, all the way around again. We'd add 2 pi to it. What do we get? 7 pi over 2. So those two places. Now what? Second derivative. Put your phone off, put it away. Second derivative. What's the derivative of negative sine x? Good, negative cosine of x. And the derivative of negative 1 is 0. What do I do with that second derivative? Yeah, we plug in those values we got. So I want the second derivative at 3 pi over 2 and the second derivative at 7 pi over 2. So I take 3 pi over 2 and I plug it into the second derivative, the cosine of 3 pi over 2. Cosine is 0, so negative 0 is 0, right? Isn't 7 pi over 2 the same answer? Yep. So what does this tell us, our zeros?
Have to do it again.
Inconclusive, we don't know.
So then you have to do the
First derivative test, yep. So we go back up here. First derivative test, number line. 3 pi over 2. 7 pi over 2. Pick some values, and where do I plug them in? Yeah, anywhere between 0 and 4 pi, and we plug them into the first derivative, right? Because this is the first derivative line. I am going to do this just to remind me kind of where my end caps are, so I don't forget. Sometimes that's helpful, especially when you're talking about trig functions, because they're circular, and so the same answers kind of start over and over, and it's kind of hard to see what's going to happen. We need something easy to plug in between 0 and 3 pi over 2, or 0 and 270. Pi over 2 or pi would be easy. Let's do a pi, why not? Take a pi, plug it into the first derivative. Sine of pi is 0 minus 1 is a negative. What's the number between 3 pi over 2 and 7 pi over 2? 2 pi, sure. So if I take 2 pi and plug it in, don't I get 0? Minus 1's a negative. What about between 7 pi over 2 and 4 pi? 3. Isn't 7 pi over 2 down here? And 4 pi is like right there? So don't we need something here? Is sine positive or negative in that fourth quadrant?
Negative.
Negative. So I have the opposite of a negative minus 1. Does it matter what it is?
Yes.
Probably matters, so you can't just plug it in. So let's see here. Let's do like, I don't know, negative 45 degrees. Negative 45 degrees is going to make this negative of, sine of negative of 45 is negative radical 2 over 2. Is that correct? Minus 1. So that's positive radical 2 over 2 minus 1. What is that? Makes the whole thing negative, doesn't it? Okay. So do we know anything else about this problem? Nope. We know that there's no relative max or min. Now, let me tell you guys, because I think this will help you out. Your assignment is not this difficult. I picked the wonky problems on purpose so you could kind of see some of the craziness that goes on, but your assignment is not this difficult. Also, I realized we did all of this by hand. There are a couple of problems on your assignment tonight. You do have a calculator. You can go graph it and find out where it crosses the x-axis to get your critical numbers. Okay? I would not do that every time. I'm not promising that we will give you a quiz where you need a calculator. I'm just saying there are some problems where use the calculator. I forgot to tell first hour that, and I started working through problems with them the next day, and one of the problems took over a page before we got the answer. And somebody's like, could we use a calculator on that? And I was like, oh yeah, we do have that resource. I kind of forgot. So, use it if you need it. Your assignment is on the board.